this lecture, we're going to work on Chapter 8. So Chapter 8 is about hypothesis testing. Now, to start off with, I wanted to show you a full hypothesis test, all neatly typed out for you so you can see the whole thing. So let me put this on the full, there, now you can see the whole thing. So this is a hypothesis test. This is our goal of learning what to do in Chapter 8, is to complete one of these, or more than one of these. Now, there are different sections to this, and I'm going to cover each section in detail and help you understand each piece. What I'd like to point out to you is if you can see the big picture, all of these pieces together, it helps you understand better of what I'm expecting you on a test. So this is actually what you will be giving me on a test. I will give you this first paragraph, which is basically your problem, and then you will have to proceed and provide me with everything else that you see here. And yes, this is possible. Yes, you can do it. It's not that bad. But I'm going to go through step by step. Everything that is underlined, claim, hypotheses, test statistic, p-value, critical value, all of those are going to be standard topics or places in your hypothesis test. Everything that goes into those is what's going to change from problem to problem, but it's still going to be a basic format that you follow every single time. So it's not a whole new picture in every section of Chapter 8. Every section of Chapter 8 is going to build and simply say, well, what if you had this situation? Then you have to change this part. If you had this situation, you have to change that part. The big picture is going to be the same. This is always going to look basically like you see here for all of Chapter 8. So we're going to do this problem here to give you an idea, and then I'm going to do one from scratch to help you. So let me go to my PowerPoint. There. Alright, so we will be doing a hypothesis test about either a population proportion or a population mean. So what does this mean? This means that they made some kind of claim about a proportion or a mean of an entire population. Here are three claims right here. The first one says the Genetics and IVF Institute claims that its XSort method allows couples to increase the probability of having a baby girl. Well, increasing probability of couples having a baby girl. That's a claim about a proportion. Okay? Meaning, in everyday language, we expect 50% of people to have boys, 50% to have girls. Well, if you increase the probability of having a baby girl, then that means you've increased the proportion that have a baby girl. Okay, so that's a proportion question. Business. A newspaper cites a pricegrabber.com survey of 1,631 subjects and claims that a majority have heard of Kindle as an ebook reader. The word majority is a claim about a population proportion again. Majority would be more than 50%. So your proportion would be, they're claiming it's more than 50%. So, is that claim true? Is that claim false? That's what a hypothesis test is going to try and tell us or clarify for us. Whether or not we have enough evidence. So in this survey of these 1,631 subjects, was there enough information to support the claim, reject the claim? What did it do to the claim? Last one. It is often claimed that the mean body temperature is 98.6 degrees. That's what everybody's been told their whole life, okay? Well, we can test this claim. That's what a hypothesis test does. It tests the claim. Using a sample of 106 body temperatures with a mean of 98.2 degrees. Wait a second. Their mean temperature was 98.2? That means some people were higher than 98.2, but some people were also lower than 98.2. Because remember, 98.2, the mean, is somewhere in the middle of the data. Well, is that enough evidence to support the claim, reject the claim that body temperature is 98.6 degrees? Well, obviously for this sample, it wasn't 98.6 degrees. So is that enough evidence to reject what everybody's always believed? That's what a hypothesis test tries to do. Alright, so here, let's go back to that problem I showed you. This is the problem, the big, full problem, but I'm taking it in pieces. So at the top we have our problem. Always start by reading your problem. So, assume that 100 babies are born, to 100 couples treated with the XSort method of gender selection. So this is one of those claims we were just talking about. Okay? So XSort method, it claimed to make girls more likely. Preliminary results from a test of the XSort method involved 100 couples who gave birth to 58 girls. So in everyday births of children, how many girls do you expect in 100 births? Well, according to our class and basically life, there's always a 50-50 shot of having a boy or a girl. Well, they had more than 50% girls. They had 58 out of 100 be girls. Well, that's more than 50. That's more than what tradition says we should have had. Tradition says we should have about 50 out of the 100 be girls. Well, is that enough evidence to say that X sort was actually effective? Yes, there were more girls, but were there enough beyond what you would expect to support X sort as, hey, they made it 8 more girls possible? Alright, that's the rest of the problem. It's going to tell us what to do. We're going to test the claim that X sort method increases the proportion of girls to greater than the 50%. Just because the sample says we got more than 50% does not mean that's enough evidence to support the X sort program. Alright, use a significance level of alpha equals 0.05. Remember, significance level is very similar to your confidence. Remember, for a 0.05 significance, meaning 5% significance, that corresponds to a 95% confidence level. Alright, here's our claim. X sort method increases the proportion of girls to greater than 50%. This is the first step in a hypothesis test. I want you to read the problem and word for word take the claim out. So where do we find the claim in this problem? Let's see. Well, it usually is very nice. Oops, oh, sorry. Let me get a highlighter. Hold on. Most of these problems are very nice, and they tell you exactly what you're going to be testing, what the claim is. So here it is. Test the claim. Usually when you see that right after, you see your claim. So here's the claim. X sort method increases the proportion of girls to greater than the 50% that occurred without any treatment. Now, I didn't write every word of that. You can shorten these a little bit, but I need you to keep the majority of the language. For example, there are some very important words in here that you could not leave out. Who are you testing something about? X sort. You have to keep that. Increases. Well, that's probably an important thing to keep. And proportion is super important because that tells you what parameter you're trying to make a test of. Population proportion. That's our P. And greater than the 50%. Well, together, number one, you need to know who you're testing about. And number two, you need to know how much. So proportion, greater than the 50%. Those are the key things you need to keep, but you also need to keep it making sense because you're going to use this at the end to make a conclusion. Better be safe than sorry. Write more rather than less when it comes to writing out the claim. Word for word from the problem, write down the claim. There will be times where the claim is not quite what you need, and you might have to go back in the problem and translate something. So they might say, increase the proportion of girls to the majority being girls in births. Okay, what does majority mean? Well, you got to go in and translate. What is majority? Majority is greater than 50%. So there will be times where you have to translate the claim a little bit, but for the most part, they're going to give it to you word for word. The problem is you do not want words. We cannot do math with words. So what you're going to have to do is you're going to have to write the claim in symbols. So when they said proportion, you should immediately realize that we are testing the P, the population parameter. Greater than is a mathematical symbol, right? The symbol. You have to turn this into symbols to do math. 50%, we cannot do math with 50%, so this is actually going to be 0.5. And that is where we get our first set of symbols from. Taking the claim and translating it into mathematical symbols. Alright? Now we're going to do the opposite. So once you have the claim as symbols, you write the complete opposite. When I say complete opposite, notice the P does not change, the 0.5 does not change. The only thing that is going to change here is the inequality. Greater than is going to become less than with an equal sign. Completely opposite inequality. If you had an equal sign, you remove it. In this case, we did not have an equal sign, so we put an equal sign on. That's the complete opposite. So those are our symbols. Now, this is the cool part. If you follow my steps, you can find the hypotheses very easily. There are 2 hypotheses. And I'm going to go through all of these again in just a minute, but I want to give you a big picture before I get into the nitty-gritty. In the hypotheses, there are 2 of them. There is the null hypothesis and the alternative hypothesis. The null hypothesis is what we usually call the status quo, traditional assumptions that probably have been made. And usually HA is what we're trying to prove true. Okay? If you want to prove something true, it needs to be in the alternative. Now, for our purposes, we are always going to let the equal sign be the null hypothesis. Why? For one, to make your life easier. But for two, the burden of proof is actually on the alternative. So we need the alternative detailed because that's where the burden of proof lies. We're trying to prove the alternative true so that we can reject the null. This is language you're going to have to get used to. I'm going to say it more and more as we go through. Now, if the equal sign is the null, then that means the opposite in this case is the null. But you only write the equal sign. The opposite symbols had the equal sign, so that one's the one you use for the null. Which makes the original set of symbols our alternative. Notice how I have marked the word claim next to the alternative hypothesis. I like to make that note here so that when I get done with my problem, I don't have to figure out where my claim was, because you're going to have to come back to the beginning. If you do not organize this, number one, you don't get any points. But number two, you won't be able to finish your problem. You've got to use the beginning, this section, at the very last step as well. Alright, now, final step here is that we are going to assume the null hypothesis is true. Well, like I said, the burden of proof is on the alternative. Why? Because we have to make this assumption. Without this assumption, we cannot do a major part in this problem. So we're going to assume the null is true. Think of this as for example, a murder trial. In a murder trial, you have a defendant. What is the assumption about that defendant? Well, court of law says he is innocent until proven guilty. So the assumption in a court of law is that they are innocent until they prove otherwise. So we are going to assume the null is true until we have enough proof of the alternative, which is actually what we're trying to prove. Remember, we're trying to prove that the proportion of girls is greater than 50%. What we're trying to prove is the alternative because we have to assume the null. Okay? Alright. I'm going to come back to these. Let me go ahead and do the nitty-gritty on what we've talked about so far. So a hypothesis is a claim or statement about a property of a population. I've already showed you a bunch of different claims or statements, and we usually write a hypothesis as symbols. A hypothesis test is the procedure for testing the claim about a property of a population. Okay, so hypothesis test. We have just gotten the hypotheses. The rest of this is the test of the hypotheses that we're trying to do. Alright, like I said, there are two hypotheses. The null is always going to have the equal sign. Now, the null can be represented with an H0 or an HO. You can also call them HO, H0, H naught, H null. But that is the null hypothesis symbol. Now, we will test the null hypothesis directly in the sense that we assume it is true. Remember I showed you that one sentence? We have to assume the null is true. And we're going to reach a conclusion to either reject the null or fail to reject the null. Okay, so in a murder trial, you're assuming innocence. So this is saying we can either reject the innocence or we can fail to reject innocence. What have I not said? I've said we can reject the innocence, meaning he's guilty, or we can fail to reject the innocence. Failing to reject innocence does not mean that the person was actually innocent. It simply means we didn't have enough proof. So we actually can never, ever, ever prove the null hypothesis is true. Why? Because we had to assume it was true in the beginning. If you want to prove something true, it has to be put in the alternative hypothesis. So this is the alternative definition. There are two different ways to denote an alternative, H1 or HA. You can use a lowercase a like I did in the notes, or uppercase. Now this is the statement with no equal sign. Okay, so it's either a less than, a greater than, or a not equals. Now, here's what I was just saying at the bottom here. Move my picture. Alright. If you were conducting a study, this is a real life situation, not in our class, okay? In a real life. If you're conducting a study and want to use a hypothesis test to support your claim, if you want to support something, remember, you cannot support the null. So, your claim must be worded so that it becomes the alternative hypothesis. Meaning you cannot have an equality. You cannot have an equal sign in your claim if you want to be able to support it. You can only support alternative hypotheses. So you want it to have a greater than, a less than, or not equals. So here are the steps I showed you of how to create your HO and H1. I already went over those, but they are here if you need to refer back to them. Alpha, in real life, you would have to select your alpha, but in all of our problems, it will be given to you. The most common are 0.05 and 0.01, so 95% confidence and 99% confidence. You might see some others in your homework just for testing purposes, but these are the most common in everyday life. So your significance level is denoted by alpha. Let's see, is there anything else I did not talk about here? Oh, this is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. So let me draw you a little picture here. So we are going to be drawing bell curves again. We'll get to that in a few minutes. Now, your null hypothesis is going to be in the large middle of this bell curve because we're assuming it's true. And it's either the population mu or it's going to be the population p proportion. Remember, mu and p are your center of your bell curve. They are measures of center for their respective distributions. Now, so your mu, your p, your HO is going to be in the middle. The critical region is where you're far enough away from the assumption to be able to reject. Sometimes you will be way over to the right and all of alpha will be in the right. Meaning, if your test statistic ends up over here, you reject the null. Other times, you will actually have two tails. So you would have to divide the alpha between the two tails. But that's what it's meaning. The alpha describes the size of this critical region. The smaller the alpha, the smaller the tails. If the tails are really small, that means you've got to be even further out from the assumption, from the null, in order to reject the null. Okay? We're going to do all this again, so just hang in there. Alright, so here are the most common formulas that you're going to need in this chapter. So, it depends on what you're testing. Are you testing P or mu? Okay? There is a variance question in the last section of chapter 8 if you want to look at that, but we're not going to test on that. Now, for proportion, you will always use the z-score, but to use the z-score, you must check for these two requirements. What are these two requirements doing? They're making sure your sample size is large enough. But not only large enough, it has to be large enough in both directions. So let me see if I can help you out here. N times P is actually the number of successes. Okay? So if your problem were to give you the language, they didn't give you N and P, but they gave you, hey, we had 58 girls out of 100 births. 58 is N times P. And you can calculate that by finding N and finding P. N times Q, on the other hand, this is the number of failures. So it depends on the language. You may have to calculate this, but if they give it to you, then don't calculate it. Now, both of these have to be at least 5 in order for you to be allowed to use a z-score. So you have to have at least 5 successes and at least 5 failures to be able to use a z-score. If you have that, this is a new formula for you. This is the z-score formula for proportion. Okay? It's very similar to the others, but the denominator is drastically different. It's technically the same thing, but instead of them having you calculate sigma and plug sigma in, they're simply plugging in P and Q and getting rid of sigma completely. Now, as for mean, there are two possibilities, just like in Chapter 7. Same rules as Chapter 7. You are going to use T or Z distribution, depending on whether sigma is not known, you use T, or sigma is known, you use Z. Don't forget, they both still require a normal distribution or n greater than 30 to do T or Z. But once you have normal or n greater than 30, then you have to decide, is it T or Z? That depends on sigma. So over here are your two formulas, your T formula and your Z formula for Z distribution, or for normal distribution, or T distribution. And those are the formulas you're going to need the most in this chapter. Alright, let's look at the next topic. So then after you have your hypotheses, you've assumed the null is true, the next step is the test statistic. This is a value used in making a decision about the null hypothesis. And it is found by converting the sample statistic to a score with the assumption that the null hypothesis is true. So I'm going to go back to our pretty picture. Alright, so here's our problem that we started with in the beginning. We've already found our claim, our hypotheses, and we've made our assumption. The next step is the test statistic. So remember that sample data they had? they had 100 couples, and 58 of them gave birth to girls. Well, that's what we're transforming. That sample data, we're going to transform it into a z-score by plugging it into the z-score formula. Now, p hat, in case you've forgotten, can be calculated by doing x divided by n. Remember, x in binomial terms, this is a binomial idea here, x was the number of successes and n was the number of trials. So in our case, they had a success of 58 girls over 100 trials, 100 births. That's where they're getting the 0.58 from. Or, no, that's right, yeah. Oh, I forgot. Check my requirements. Sorry, I forgot to do that. Okay, remember, to do a z-score or a t-score formula, you have to check your requirement. For a z-score formula, and we're doing z here because we're doing a p hypothesis test, you have to check for two things. You have to check that n times p and n times q are both at least 5. Well, they actually both end up being 50. 100 trials, 100 births, and p, where did I get p from? Let me go back. Here's p. Remember, we assumed that p was 0.05. Because of that assumption, we are able to plug that in right here, 0.5. Okay? So, because of those two numbers being at least 5, we can continue and we can use our z-score. Now, this is the z-score formula I showed you on that table, which is on your formula sheet, don't forget. You plug in your p hat, you plug in your p. These two are mixed up a lot. Make sure you look at your formula sheet and use your formula sheet. Make sure you get them in the right order. If you have them in the wrong order, you're going to end up with the wrong sign in your problem. In the bottom, you're going to use p and q, not p hat and q hat. P and q. Plug them in. So these are, oh, I guess I should remind you where to find q. Remember, q is 1 minus p. So that's how they got the other 0.5 here. 1 minus the 0.5 leaves you with 0.5. Anyway, that is your z-score formula. So here's our z-score, 1.60, and now we have two methods of how to approach this. So let me show you them. These are the two methods, p-value and critical value. Now, they are very different, but they are doing the same job. They will give you the same answer. So it does not technically matter which one you use in real life. I prefer critical value because it gives me a picture and I can see my decision. P-value, some people prefer that one because it doesn't require a picture necessarily, and you're able to simply memorize a couple situations and you're done. So I'm going to go over these with you, but this is almost done with the hypothesis test here. So let me go back to where we were in the notes. Alright, so here we go. Already did that. Okay. Oh, yes. Alright, so before I can do a p-value or a critical value test, I need to make sure you understand the tails. The tails in a distribution are the extreme regions bounded by critical values. So determinations of p-values and critical values are affected by whether a critical region is in two tails, which is what all of Chapter 7 was, or one tail. It could be a left tail or a right tail now. And that's the major difference between Chapter 7 and Chapter 8 in terms of z-scores and t-distribution values. Sometimes you'll have one tail and sometimes you'll have two tails now. In Chapter 7 it was always two tails. It therefore becomes important to correctly characterize a hypothesis test as two-tailed, left-tailed, or right-tailed. Here we go. Alright, so here we have the hypothesis, HO and H1, or alternative. And notice I have equal sign and not equals. So I didn't worry about an example here. I just wanted the symbols, just to clarify what the symbols tell you about the rejection region. Notice, here I'm going to show you all three. 1, 2, 3. There are 3 of these. All 3 of them have the equal sign for the null. That's because it always is an equal sign. To discover how many tails you're dealing with and which tails, you have to look at the alternative. The alternative hypothesis in this case is not equals. What does that mean? That means it could be bigger or it could be smaller. Meaning either direction away from the null, remember I told you the null is in the middle, either direction from the null, we would have enough evidence to reject the null. Okay? That is why in this picture you see there are 2 tails. If you have a not equal sign in the alternative, you have 2 rejection regions. Now alpha, like I said earlier, is divided equally. So this area here would be alpha divided by 2, and this area here would also be alpha divided by 2. Together, they make a total of alpha area in the rejection regions. Excuse me. Alright. In this case, the alternative has a less than sign. A less than sign, for example, it would say mu is less than 26. The mean being less than 26 means that we have a left-tailed test. So a left-tailed test implies that all of alpha is in that one tail. Okay? A less than sign, left tail, all of alpha is there. For a greater than symbol, that means we have a right-tailed test and all of alpha goes in the right tail. Those tails, left tail, right tail, if your sample, your test statistic, is all the way in either of those tails, depending on which problem you're in, that is when you would reject the null hypothesis. Okay? Alright, so here are the scenarios for p-value. So the p-value is also called a probability value. If you're going to write p-value, you must write p-value. Capital P, lowercase p does not cut it. Those have different meanings. Those mean proportion or probability. P-value means p-value. You have to write the whole thing. So p-value is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So you have the sample data. This is the probability of getting a number that big or bigger. Okay? So, critical regions in the left tail or right tail. In either one of those cases, your p-value is the area in that tail. Okay? Now, I want to point this out to you. When you calculate area of the tail, you calculate it in reference to your test statistic. So in other words, if you were to draw a picture, here's my picture, it's horrible, I'm sorry, and your z-score, your test statistic was here. Now this is not a critical value, this is just your test statistic. Your test statistic is this guy right here. Now, this is a left-tailed test. Why? Because my hypothesis said so. Look at your alternative. This area here is your p-value. In a right-tailed test, your z-score would probably be somewhere closer to the right, and your area in that tail would be your p-value. For a two-tailed test, you're going to have a test statistic. You're only going to have one. So your test statistic could be in the left or the right. I don't know. Okay, so here, I'm going to mark my test statistic. You have this area in this tail. But because this was a two-tailed test, you actually have to double that area. So this area here, we have to multiply by 2 to get our p-value, because it was a two-tailed test. So those are how you calculate your p-value. You find your test statistic, like I already showed you. You find the area to the left or the right, the tail. You have to check which tail you're interested in according to your alternative hypothesis. Here's a little guide to help you determine what type of test, left-tailed or right-tailed, and then how to find your p-value. Basically, I like to draw a picture. I'm a picture person. Otherwise, you memorize these. Remember, if it's a two-tailed test according to your alternative, if it was a not equal sign, you have to double your p-value, or double your area to get your p-value. Otherwise, you just find the area from your test statistic in the direction of the tail you're trying to do a test on. As I said, don't confuse p-value with a proportion p. They are distinct, they are different. P-value is the probability of getting a value at least as extreme as your test statistic. P is the population proportion. It's the actual proportion. It's not a probability, it's an actual proportion of the population. Alright. Where is my critical value? Good question. Alright, hold on. I gotta make sure I'm not missing something. Okay, so that was p-value. Now, before we go to this, let me talk about the critical value method. Okay, so the critical value method is simply one little picture. Let me show you what picture you're going to draw. You're going to draw either a right-tailed picture, like this illustration here, or a left-tailed picture, or a two-tailed picture. Now, for critical value, you have to go to your alpha and decide how big those tails are. So let me go up to our example. That's the easiest way. Alright, here's our example. in the example we were doing for XOR, remember we had for our alternative, here's our alternative hypothesis right here, a greater than symbol. Because it was a greater than symbol, that means we have a right-tailed test. So for our critical value method, if we chose this over p-value, you would draw this picture here. Now this area should be shaded here, but my computer wouldn't let me do that, so let me shade it now. So we would shade this area here. This is the rejection region. This is where we would reject the null. The size of this region is determined by alpha. Once you have your alpha in the right side of your bell curve, or it could be both sides, then you look up the z-score corresponding to that area. So we would want to look up this z-score. How did we get this z-score? Well, think about it like this. If there's 0.05 to the right, that means there is 0.95 to the left of that critical value line. So this is area. If you look up this area on the positive z-score table, then you would find this z-score here. Now this z-score is familiar from chapter 7, but remember chapter 7 had 2 tails. So this is not going to match anything you memorized from chapter 7 because this is a one-tailed test. So 1.645 is what we call our critical value. And that's what you have to do. You have to find the critical value, that number, that critical line. Now once you have that critical line, you then go back to your test statistic. Remember our test statistic was 1.6? Well, where does 1.6 fall in this bell curve? Well, it's smaller than 1.645, which means it falls to the left of our critical value. Left of our critical value is where we fail to reject the null. Okay? So that's how you finish a critical value method. So let me go back to where we were. And we are going to do more examples of these. So if anything doesn't make sense here, just be patient. You have lots of examples in this chapter. Where am I? There I am. So the methodologies of p-value and critical value, I showed you both. Okay, p-value, you start with your test statistic. And from your test statistic, you get the area and the tail. Critical value, you start with your alpha and get the area and your tail corresponding to the alpha. Now, how do you make a decision? If your p-value is less than or equal to alpha, you would reject the null. That's it. This means your p-value is small. There's a very small chance of this or bigger happening if your null hypothesis was in fact true. There's such a small chance that it should not have happened. That's what's basically happening here. If your p-value is less than alpha, it should never have happened in the first place if your null was true, which must mean your null is not true, so we reject the null. If, on the other hand, your p-value is larger than alpha, meaning there's a very good chance of that value or a bigger happening, then, well, we would fail to reject the null. It's very possible that it or more extreme could happen. So that's how you take a p-value and make a decision. For critical value, I already showed you basically, if the test statistic, the z-score, falls within the critical region. Remember, the critical region is determined by alpha. So alpha, draw your shaded area, get your critical value. Then you take your test statistic. If your test statistic falls in that critical region, you reject the null. If, on the other hand, it does not fall in the critical region, the tail, then you fail to reject the null. Those are the two possibilities. Finally, we need to state a conclusion. Now, yes, we have a conclusion here. We reject or fail to reject the null. But that's not English, that's not everyday language. So I need you to put this in terms of the original claim. So that's our goal here. This is a mess, it looks like, but it helps a lot in understanding how to word your final conclusion in terms of the claim. I do not want to know about the hypotheses here. I want to know about the actual claim that you started with. What did you conclude about the claim? Remember, your claim is not the null hypothesis necessarily. It's not even necessarily the alternative. You have no idea at this point. All you worked with was HO and HA, the null and alternative. Now you got to go back and say, okay, I have my conclusion about the null. What does that mean about the original claim? Here's how you do it. Now, first of all, does your original claim contain the condition of equality? Okay, if yes, then that means your claim was the null hypothesis. Okay, so if your original claim had equality, then your HO is the claim. Now, if that's the claim, did you reject it? If you rejected the claim because it was your HO, there is sufficient evidence to warrant rejection of the claim that, and then you write the claim out that you wrote at the beginning. This is why you pulled the claim out at the beginning, so you could put it right here and finish your problem. Okay? Alright, now, if HO is the claim, and you did not reject it, you failed to reject the claim, you failed to reject the HO, you failed to reject the claim, then there is not sufficient evidence to warrant rejection of the claim that, and then you write your claim. So what this is saying, there is not sufficient evidence to warrant rejection. We can't support the claim, but we didn't have enough evidence to throw it out. Okay? So in a murder trial, this would be the situation whereas, well, I couldn't prove him guilty, so we had to let him go. They didn't show that he was innocent. That's not the burden of proof. The burden of proof is on the alternative, not the null. Alright, now, if your original claim does not contain equality, then your HA is the claim. The question then is, do you reject HO? Notice I'm still asked about HO, not HA. Do you reject the null? If yes, you rejected the null, then what does that mean about the claim? That means you're able to support the claim. You rejected the null, so you're supporting the alternative. The alternative is the claim, so you're supporting the claim. Okay? Finally, if your alternative is the claim, and you failed to reject the null, then there is not sufficient evidence to support the claim. Okay? You still can't actually support the claim. You simply say there's not sufficient evidence to actually support the claim. Okay? Alright, so we see what else. Caution, never conclude a hypothesis test with a statement of reject the null hypothesis or fail to reject the null hypothesis. You must refer back to the original claim in your final conclusion. So just be careful with that. Some texts use the words accept the null hypothesis, and I've told you over and over again, you never accept the null hypothesis. This is because we're not proving the null. We've actually had to assume it to be true. Fail to reject says it more correctly because of that reasoning, that the available evidence is not strong enough to warrant rejection of the null hypothesis. It's not that we're supporting it. It's not we're accepting it. We're simply failing to reject it. Okay? Now, a big part of why we avoid to accept the null hypothesis is because there are two types of errors that can occur in a hypothesis test. Hypothesis tests don't tell you black and white whether this is right or wrong. It gives you an idea based on the sample whether you should support something or reject something. But it's not actually telling you it's right or wrong. It's simply support or we suggest you reject. Okay? Here are the two types of error. Type 1 error is the mistake of rejecting the null hypothesis when it was actually true. Should you reject something that's true? No. That's an error. The symbol alpha is used to represent the probability of type 1 error. The smaller the alpha, the more evidence you need in order to reject the null. Well, the more evidence you need, the less chance of making an error. So the smaller the alpha, the smaller the chance of making a type 1 error. Alright, type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. So this is basically, we are avoiding, when we avoid this type of error, we're avoiding accepting the null hypothesis when it was actually false. Okay? So here they kind of make it a very safe answer, and this is why we say we failed to reject the null when it was actually true. We didn't actually accept it. We simply said, well, we can't reject it. It's a play on words. The symbol beta, this B symbol, is used to represent the probability of a type 2 error. Now beta we will not calculate. That's a further course you can take in statistics, but it is something that you can try and minimize in the future. But for our purposes, to minimize a type 2 error, we simply never accept, and that kind of avoids it. Alright, here is the little flowchart of what you can expect. So you have a couple conclusions. You can reject the null hypothesis, or you can fail to reject the null hypothesis. Those are pretty much your two conclusions that you'll have in a hypothesis test. Now, if you decide to reject the null hypothesis, when in fact the null is true, you rejected the truth, that is an error, type 1 error. Okay? If, on the other hand, you decided to reject the null hypothesis when it was false, you made the right decision. You rejected the false statement. Okay? Now, what if you were to fail to reject the null hypothesis when the null hypothesis is true? You made the correct decision. You failed to reject the truth. You didn't accept it, which would be better, but remember, we're trying to avoid a type 2 error, so fail to reject is safer. Now, what if you failed to reject the null hypothesis when the null hypothesis is false? You failed to reject something that's false. That's an error, type 2 error. Okay? So you should see that there's only 4 possibilities. In 2 situations, you make an error. In the other 2, you get the correct decision. Remember, we've minimized type 1 error by making alpha small. And type 2 error you can minimize by minimizing beta, but that is another course that you can take. It is minimized as far as we can in this course, but alpha is our main priority right now. Alright, I want you to identify a type 1 error here. So here's our example. Let me move this out of the way. Assume that we are conducting a hypothesis test of the claim that a method of gender selection increases the likelihood of a baby girl, so that the probability of a baby girl is greater than 0.5. This is our problem that we were working on earlier. Now, what would be a type 1 versus a type 2 error in this particular problem? Here are the null and alternative hypotheses we already wrote down. So, a type 1 error. Let me go back. Let me clear this. Alright. So, what would a type 1 error be? Type 1 error is when you reject the null when the null is true. So in this question, a type 1 error would be when we reject p equals 0.5 when in fact p does equal 0.5. That would be a type 1 error. You can, let's see. Now, okay, so in words, what are we doing here? We are rejecting that the status quo is the status quo. That we're rejecting that the proportion was actually 50-50 of boys and girls, when in fact it did end up being a 50-50 of boys and girls. Now, in type 2 error, this is when we fail to reject the null hypothesis when in fact HO is false. So, we fail to reject P equals 0.5 when in fact P does not equal 0.5. Okay? You can also phrase these in terms of the alternative, and you probably see that on your homework a little bit, so let me just clarify. If you fail to reject the null, then that means you are if you fail to reject the null, let me get straight in my head. You're just going to have to read it when you question. This one I can't do because I don't have the words in front of me. All yours are multiple choice on your homework and on the review sheet, etc. You're going to have to read it. Sometimes they're going to phrase it in terms of the null hypothesis. Other times they're going to turn around and phrase it in terms of the alternative hypothesis. So instead of rejecting the null, they could say they accept, there we go, that's what I'm thinking, the alternative, HA. When in fact, let's see, what's the opposite? Let's see, they reject, when in fact HA was false. There, that's the complete opposite of what they stated in terms of the null. So these can be stated in terms of the null or the alternative. You're going to have to read and practice understanding what are they using. Are they using the null or the alternative? So here you go. Nicely typed up version. A type 1 error is the mistake of rejecting a true null hypothesis. We conclude the probability of having a girl is greater than 50% when in reality it's not. So see here, they actually use the alternative. That's what I was trying to get to. So they conclude the probability of having a girl is greater than 50%, meaning they rejected the null. When in reality it's not, meaning in reality the null was the truth. Okay? A type 2 error is the mistake of failing to reject the null hypothesis when it is false. There is no evidence to conclude the probability of having a girl is greater than 50%. Okay? So here again, they're talking about the alternative. There's no evidence to conclude the probability of growth is greater than 50%. But in reality, the probability is greater than 50%. So that would be a type 2 error. Okay? They said there was no evidence to support the alternative, when in fact, the alternative was in fact true. So you can state these in terms of null or alternative. Alright, that's 8.2. I'm going to stop this video. Make sure you do your homework before you continue. It's important that you understand the pieces, and 8.2 is all about the pieces before you continue to 8.3, where we start doing full-out problems. And remember, you're going to have examples in your review sheet, and you're going to need to look at those to get ideas of how to organize. And your homework is a piecewise problem. Part A, Part B, Part C, Part D, which is good for homework because it helps you a lot. But it's not like that on the test. On the test, you're going to have a paragraph at the top and then a blank sheet of paper where you're expected to put all the pieces, just like you saw in the original example I showed you. Let me show you that again. So this is what you will need to practice doing so that when you get your test, you can present this to me on your test. So I will give you this top paragraph. You will have to make up the rest of this. And by practicing, doing your homework, writing down your homework, write down the problem, then the claim, and the hypothesis, the test statistic, that'll help you a lot. Not necessarily in this homework, 8.2, but in 8.3 and 8.4, you've got to practice writing it like this. This is what I will expect, because this is an organization problem. Alright, so go do your homework, and come back to watch the next video.